A lot of you are thinking that magnetism is just the craziest, hardest, most complicated thing you've ever encountered. And I'm here to show you that it's really simple. I'm going to try to paint the picture, the big picture, of the magnetic force. It's important to think of this magnetic force, or magnetic push, as a two-step dance. Something creates a magnetic field, step one, and then that magnetic field pushes on something else, step two. Let's look at step one. There are only 3 ways to set up a magnetic field. 50 ways to leave a lover. 3 ways. Okay. The first way is with a bar magnet. And what we found is that the magnetic field lines come out of the north, wrap around and go into a south. Out of a north, wrap around and into a south. Now, typically when we're using a bar magnet, we're using the poles. We're either near a north pole or near a south pole. And so what we really care about is away from a north pole and towards a south pole. Okay? That's way number 1. Way number 2 is with a solenoid. If I have a bunch of coils, and let's say the current is going into the board at the bottom and out of the board at the top. So this is one current. It goes in and out, in and out, in and out, in and round and round and round. Now, we can use right-hand rule number 3 to define the north pole of that solenoid. We put the curved part of our hand in the direction of the coil. Our thumb is pointing in the direction of the north side of that solenoid. That's also the direction that field lines are going through the solenoid. They come out of the north, wrap around, and go into the south. Out of the north, wrap around, and into the south. Now we know from superposition that a solenoid is just a bunch of loops. And in a loop, the field goes through. And so that tells us what the field lines do inside of the solenoid. Outside they go from north to south. Inside they go from south to north to finish the loop. Okay? Now because a solenoid and a bar magnet act exactly the same, because the bar magnet is just a kind of a solenoid, we know that field lines inside a bar magnet also go from south to north to complete the loop. Now that's where it's dark. We can't put a compass. But by using this analogy with the solenoid, we know that these field lines, if they come out of the north, go into the south, they have to keep on going back to the north. Okay? So that's way number 2. Way number 3 is if I have a long, straight, current-carrying wire. Okay? If that's conventional current coming towards you, I know by right-hand rule number 2, the field lines are going to be circles that go around that. By right-hand rule number 2, I can remember which way they wrap around. I use the straight part of my hand to represent the straight current. My fingers are curling in the direction of the B field line. Now the B lines paint the picture everywhere, but if I just want the magnetic field there, it would be a vector that is tangent to the line. If I wanted the vector here, it would be a direction tangent to the line. Those are the 3 ways to set up a magnetic field. That's step 1 of the 2-step dance. The next step is that the magnetic field pushes on something else. Well, one way is to push on a moving charge. If I have a magnetic field that's pointing towards that open door, and it's a uniform magnetic field because the field lines are evenly spaced, if I have a positive charge that is moving across those field lines, I'm going to have a magnetic force. That magnetic force is going to have a magnitude QVB sine theta. And since we're looking for the magnitude of that force, we use the magnitude of the charge. If it's an electron, we never put a negative 1.6 times 10 to the minus 19 there. We just want to know the strength of the magnetic push. Now the direction of the push is given by which right-hand rule? Number 1. We've already used 2 and 3 up there. Now, again, I reach in the direction of the motion. I turn my wrist in the direction of the B field, and so I can wave in the direction of the B field, and that's my angle theta. And so the force here would be into the page on a positive charge. Now, the second way that we can push on something is if we have a wire carrying charge. Well, if each of those charges is pushed with a magnetic force, so is the wire. So if I have a magnetic field towards the open door, again, and I have a wire, let's say it's got a green coating on it, and that wire is carrying conventional current this way, and let's say that that wire is length L, then the magnetic force per unit length, the total push is going to depend on how long the wire is. So if you just want the push per unit length, it's going to be the current times the B field times the sine of the angle between them. You're never going to use that formula, okay? But I just wanted you to see it. You are going to use the fact that the direction of that force is given by right-hand rule number 1. And again, the force would be in all along the wire. Okay. Now the last 2 cases both deal with a push or a pull on a bar magnet. In the first case, we have a uniform magnetic field, by which I mean field lines that are evenly spaced. If I lay a bar magnet down in that, I can think of that north pole as the arrowhead on a compass needle. That compass needle is going to turn around, it's just going to rotate and line up with the B field. Now I can think of that as happening because the North Pole is being pulled in the direction of the B field and the South Pole is being pulled in the opposite direction. Now, if the field is uniform, that's going to rotate the bar magnet and now I can think of those forces on the north in the same direction as B, in the south in the opposite direction. If these forces are equal and opposite, it doesn't go anywhere. It just lines up and stops, like a compass needle. Now the last case is super interesting. If I've got a magnetic field that is not uniform, and those field lines aren't parallel, this would indicate a strong magnetic field and a weak magnetic field. This would be the kind of field lines I'd have near, say, a south pole. Either the south pole of a bar magnet or the south pole of a solenoid. Now if I lay a bar magnet down, and I use the idea that the north is pulled in the direction of B, south in the opposite direction, this bar magnet is going to spin around and line up with the field. And here's what makes this different. The north pole is in the region of a strong magnetic field. It feels a big pull. The south pole is in a weak magnetic field. It feels a small pull. And this thing's just going to get sucked in to that pole. But you knew that since the 3rd grade. If you have a great big south pole sitting on your table, and you lay a little bar magnet down on the table, it's going to quickly flip around so the north is towards the south, and then it's going to suck clear across the table until it goes clang and hits it. Now I can demonstrate that. This is really, oh man, we got 3 minutes. This is going to be the best 3 minutes of your life. I have here a solenoid that's going to generate, when I hit this switch, a non-uniform magnetic field. That's going to magnetize this bar magnet and suck it in. Watch. Now, why would you want to do that? Well, at University of Washington, they had a great big coil, huge coil, and they had it hooked up to 14 12-volt batteries to get a huge current. They had a great big iron core, and they would start with 2 feet of it outside of the coil. When they pushed the button, it would come zipping in, just really fast, zip it in, and just stay in the middle. It didn't take us very long to figure out that if you push the button, get it zipping in, and then release the button when it gets in the middle, it went right out the other side, and it's a rail gun. Yeah. Now, we got 1 minute. Hold on. Will you give me 2 minutes? Thank you. When you turn on your car, you're going to need 75 amps to turn over your engine. Trust me, you don't want 75 amps going through your steering column. That's dangerous. So what we have on top of the starter is a solenoid, just a coil. That solenoid has an iron plunger in it, and that solenoid is hooked up through the ignition. So that when you turn your key, you send a little bit of current through the coil. That magnetizes the solenoid and drags that iron core down into the center. They use that to close the real switch that has the 75 amps in it, so that you don't have to get anywhere near that. Now, a fellow has used that idea to make a very clever device. Okay. All he's using is a little copper wire, some magnets, and a battery. He puts magnets on either side. They have to be either north towards north or south towards south. Now, watch what else he can do with this. Okay, it gets better. Oh yeah, okay. Okay folks, have a good weekend.